Cool. Awesome. So what am I doing? I am learning Haskell, and so I found this course that's called the FP course. Let me go to it. Close this Reddit page. Never mind that. So this page on GitHub, which you can find at system-fp/fp-course, is a linear progression Haskell course. So basically, it starts off with basically nothing, just very basic syntax of the language. And you start re-implementing core parts of the language. Not because that's a good idea, but because it helps you to learn it. And Haskell, at least in my opinion, has a very high learning curve. So last time we went over some of the first beginning modules. So let me open up the README here. And please tell me if there's like anything I can do to improve the video or the audio or the text size or whatever. So we went over like where you can install Haskell, and we went over some basic commands like how to open up a REPL so you can do some basic Haskell commands in your terminal. And let's see, what else did we do? We went over these introductory modules called exactly one and validation. And then I accidentally skipped over this optional one because it wasn't in this list. So it's okay. It says you don't have to do them in order. So I think what I'll do is I'll kind of get everyone up to speed on where I got in the list module. And then we only solved a few exercises in there. And then based on how fast it went before, we probably won't even finish the list module, or we might. I guess we'll see. So let's dive in. And please, if you have any questions, if you're like, what is Haskell? What is a function? Please just let me know. I'm happy to explain anything and everything. Not that I'll be able to, but I will do my darndest to explain it to you. Okay, so what we talked about last time is we implemented our own data type called list. And that's this data keyword is basically saying I'm defining a new data type called list that's parameterized by some type t. So this is kind of like I don't know exactly the right term to put it. Parameterized type. I just come from Ruby and JavaScript, a humble dynamic programmer. But basically, there are two ways to make a list. You can use this constructor, nil. So you type literally those characters with a capital N. So let me open up my REPL here. And I'm really doing the font like as big as I can bear to have it because I know it's annoying to have small font. Algebraic, yeah, Pluminator says algebraic data type. Thank you for saying it. It was getting past me. Algebraic data type. I guess what is that in what's in that a contrast to? Like what would you call it? What would you call like a type in Java or a language that doesn't have algebraic data types? Maybe I should just look up. Data types. I've heard people talk about this, so I could just copy what I've heard people say, but I want to try to explain it in my own language. Algebraic data type is a kind of composite type formed by combining other types. Two common classes of algebraic types are product types and sum types. Okay, that's starting to. I'm somewhat familiar with that kind of notion. Bobo Malone says I remember a short bit on Haskell from college and something about a function different from a method and how those words have actual meaning. Yeah. Winners is what makes it algebraic is having a product and a sum. Okay. Java has products but no sum. They're different in Haskell because they're unmutable. So I think there's multiple kind of concepts that we're talking about. So what's the difference between a method and a function with regards to Haskell? So I think the notion of a method comes from class. Like in object-oriented programming, a class has a method. So you have class methods and instance methods, whereas a function is just a function. Like it like a mathematical function is just basically something that takes a value and transforms that value, or maybe doesn't. It just has some input and has some output, like what you learn in like algebra. Whereas like a method, well, I guess in the early history of programming, you have like a procedure, which is just more like telling the computer exactly what to do, just giving it instructions. And then eventually, I mean, I'm just kind of speculating, but um, I think the difference between a method and a function would be in that in Haskell, um, a function is like a pure mathematical idea. So maybe we can demonstrate this a little bit. So last time we talked about how we could have this function like add x, y, and then we could say x plus y. So I could bump that up a little bit. This syntax looks really weird if you're used to other programming languages. But basically, you're saying the left-hand side, I'm defining a function add that takes two parameters, x and y. And this expression is equivalent to this expression. So if I say add 1 and 2, this is the same as this expression where x is 1 and y is 2. Whereas like in a method, in other like object-oriented languages, you can't just have that kind of substitutional equality like that. And that allows for some very powerful things, the implications of which I don't fully understand. Pluminator, do you have any anything to add to that? Yeah, let's go back to one of Phobo Malone's questions. Are they different in Haskell because they're full? So values are immutable in Haskell, but I don't think that necessarily has to be the case with a function. Well, I guess some language like JavaScript has the keyword function, but that doesn't obviously doesn't mean that it's a pure function. Whereas in Haskell, um, ah, getting a pager duty alert, hilarious. Better check that. Might be a short stream, guys. Sorry, there's literally like ringing in my ears. Oh yeah, okay. I don't have to worry about that. Okay. Rave Slime TV said automatic currying is awesome too. Yeah, so let's go over that. We went over it a little bit last time, but I think we have some different people. So I've made this add function, and I can add two numbers together, and I can inquire about what the type of add is. And this type signature is a little annoying, so what I'm going to do instead is I'm going to define it here, so I can define my own type signature, and I'm going to say add is a function which has the type of, you can read these two colons as it has the type of integer to integer to integer, thrilling stuff. And then now that I've defined the signature of the function, I'm going to define the implementation. I don't know if that's the correct language to use, but so now if I save this, the reason I didn't do this in the REPL is just annoying to do like multi-line statements like that. So now I can load source list.hs, which is this file over here. And I should have this add function. Yes. So add is a function that goes from an int to an int to an int. So we can think of this as in two ways. Basically, we could think of it as, let me see, last time I had all of these like pop-ups, like VS Code was like spamming me with pop-ups. See if I can disable that. Still disabled. I guess it's just like the Haskell extension being very eager to show me type information. I find a little bit annoying, but we'll just roll with it. So I could think of this add function as this, basically. It takes two integers and it returns an integer, which is certainly true. So if I give add two integers, 2 and 4, it adds them and returns an integer 6. But I can just as easily think of it as this. This is also a valid way to think of it because there's no parentheses around this. Like you could explicitly add parentheses like this, and that means something else. But I can think of add as a function which takes an integer and returns a function which takes an integer and returns an integer. So let's try this out. So I could say add 10 is equal to the function add applied to a single argument 10 and hit enter. So in most languages, this would just blow up. It would be like an exception, like you only provided one argument when I was expecting 2. But in Haskell, these all functions are automatically curried. So what does that mean? I can look at this add 10 function. You can see add 10 is a function which takes an integer and returns an integer. So it's like we've provided this first integer which in our case is a 10, and we've stored that in this x variable, and it's just hanging out there, kind of captured or closed inside of this add 10 function. So now we can provide add 10 with an integer, say 20, and that will give us this final integer. So it's I really like this syntax, and I think it's very elegant. I mean, it's very easy to read once you get used to it. It's like you can just quickly see what a function does. So these functions, this is going to take a bit of getting used to. Let me try to see. Like this is a simple example. So it takes some value of type A. We don't know what the type is. And then it takes a list of elements of type A, and it returns an element of type A. So it's just really easy to see what's going on, my opinion. So that's what automatic currying is. So, and I also wanted to mention there's this uncurry function, which itself, see, we can look at the type of uncurry. And basically, uncurry takes a function from A to B to C, and let's see, I guess this, you could say it takes a function a to b to c and then returns a function from a pair ab to c. So new add equals on curry add. Now if we look at new add, we'll see it has this pattern. So new add takes two integers and returns an integer. And if we give it just a single integer, it will blow up and say you only gave me one argument and I expected two. Yeah, so that's a bit of a introduction into like the syntax, which we went over some of last time. And actually, I think the README has a whole section that I neglected to mention. Yeah, this introducing Haskell thing. This section is a guide for the instructor to introduce Haskell syntax. We talked about the has type. One thing I didn't mention last time is how to construct lambdas or basically anonymous functions. So I can just say, the foo equals, and then I'm going to basically I'm going to construct a new function. I'm going to say it takes an x and a y and adds them together. So this backslash here is how you denote a lambda expression in Haskell. So this side is the arguments, and this is the function body. I think they did the backslash because it it's supposed to look like a lambda. So it's basically the same as add here, and I can look at foo, and it's it's the same as add basically. Rave Slime says rip Haskell curry. Yes, indeed. The guy that Haskell's named after, his full name was Haskell Curry. So currying is named after him. But apparently there's some mathematician named Sean Finkel that created the concept of currying before Haskell. So maybe we should call it Sean Finkeling. What I've heard. Yeah, lambda calculus. Interesting stuff. Operators. We talked a bit about operators. Backticks, data keyword. Would it be helpful if I go over basic syntax, or should we just go into more exercises? I'm kind of keen to just get into the exercises, and if people don't understand the syntax, please just let me know. I think that's what I'll do, and unless someone screams out in the chat, says otherwise. Okay. So we went over this fold right function. I'm gonna delete the font. Fold right, we talked about how it's basically constructor replacement. So if I have a list, we construct a list with this syntax, which is the way that we defined it in our custom list type. So we can construct a list using this nil keyword. So that's my list equals nil. And if I look at my list, it says it's a list T. Or I can construct a list of integers or numbers by saying, list equals 1 nil. Got it. There's also a list T where T is some number, like so. And the reason we have to end our list with this nil constructor is because of this recursive definition. So to construct a list, we either give Haskell the nil keyword, or we give it a value of type t and use this operator, which is like the cons operator, or append, and we append some value of type t onto a list of t's. So I could do that and say, okay, well, I'm going to construct a list. But if I use this constructor, now I need to give it a list t to append it to. So I can add another element. That's like saying, okay, I have to add it to a list, so now I need to make a list. Well, now I just need to keep adding a list onto the end, and until at some point I just have to add this nil keyword to terminate the construction of my list. So it's a little bit weird. In a regular Haskell, the built-in list type, you just basically provide this syntax instead of nil, which I guess I can do here as well. Okay, so that's how we construct a list. Fold right is like a function that, the way I think of it is like taking the last two values of a list and giving some operator to fold right and saying like, use that operator in the last two elements, and then that's your new last element, and then do the two last elements again. So for example, we could say fold right plus 0, and then we could pass in list 1, 2, 3, nil. And so fold right is going to say 0 is like my starting element. So take the 3 and the 0 and add those together. We get 3. That's our new last element. Then take 2 and 3, add those together, then we get 5, and that's our new last element. And then 1 and 5, add those together. And that's how I think about fold right in the context of JavaScript. Or I guess JavaScript's reduce actually goes left to right, but it's kind of the same thing. But it's maybe a better intuition to develop, to think of fold right as a way of replacing this operator. So constructor replacement. So we can say, the first argument to fold right is some function or operator that we want to replace cons with. And the second argument to fold right is what we want to replace nil with. So if we look at this example, we could say, it looks like I did this example here. So just copy this. I think I said, so I start with this list. I said I'm going to replace the cons operator with plus. I'll do that. And then I want to replace nil with 0. And I get this. And that equals 6. So that's a helpful intuition to build. Fold left is more like a for loop, and it's not lazily evaluated. In other words, imagine you're folding left over expressions like calculate some element of pi is the first element of the list, and then calculate some other thing is the second element of list. Fold left is going to immediately do that calculation and then continue, whereas fold right is lazily evaluated. Maybe that's a little bit getting too far ahead of myself. Head_or is this function that either returns the head of the list or some default you pass in. So that could be useful in case the list is empty. So you can say head or 3 nil. That gives me back 3. or I could provide a list 1, 2, nil, clear the terminal here, and that will provide me the first element of the list, which we typically call the head of the list. And the way that we implemented this was by using pattern matching, which is really a really awesome language feature. Once you use it, I think it's really hard to go without it. I was first introduced to pattern matching like through the Elixir language. So what it's saying is, well, let me just demonstrate this again. So I could say I'm going to define my own function called is1, and it takes some argument. If the argument is 1, I say true. And my Haskell plugin is being helpful in suggesting a type signature for me, which is pretty cool. So if the parameter is any other value, we'll say false because it's not a 1. Let's see, there's the type signature. So I'm just going to change the type signature to say type information, like so spammy. It takes an integer and returns a bool. So if you provide the function with a 1, return true. You provide the function with any other value, return false. And it's hlen is telling me you define this x variable, but you're not using it. So what I can do is I can just put an underscore here to say I really don't care what the value is because I know it's not a 1. Because if it was a 1, it would have pattern matched on this expression already. So we can demonstrate this by reloading the terminal, saying is1 and variable not in scope. Oh, I didn't save the file. Reload is1, that's true. 1, anything else, it's false. And so basically, when you pass some argument to is1, it's going to look from the start top to bottom and say, okay, is1 was passed to 5. Does this expression match that? No, it doesn't. So keep going. Does this expression match it? Well, yes, because this underscore is like a catch-all. Every value will match that. And it says, okay, how do I implement this? I return false. So that's our is1 function. So what's going on with headOr? Well, headOr is saying I'm taking one value of type A. I'm going to call that x, and then the second argument pattern matching on an empty list with this nil constructor. So this first expression will only match if the list is nil or if it's an empty list. In which case, we just want to return x, which is what we demonstrated above here. Just want to return x if this is nil. If the list is not nil, then we can pattern match using this. So we know the list was constructed with our cons operator, which means there must be a first element. So I can kind of demonstrate this by saying h e equals some list, right? So nil, and it's warning me your pattern matches are non-exhaustive because I didn't check for the nil case here. So that's a helpful warning there, but it still worked. So if I look at what h is, it's 1, and t is the rest of the list. Maybe I should do a longer example. There. So h is 1, t is 2, 3, 4. And just to demonstrate, we can do we can match multiple times like this. Say 1, 2, 3, 4. No. So this is going to match the first argument. This is going to match the second, and then this will be the rest of the list. So x1 should be 1, 2 is 2, then t is the rest. And so if there were only 2 elements, this would fail because it wouldn't match. I think. I'm not lying. Oh, t is going to be nil in that case, so it would match. So if there's only one element in the list, then we look at t, we get an exception, right? Because x1, yeah, it couldn't match this pattern. We throw an exception. Okay, I think I've beaten that horse to death. So are there any questions? Maybe you can tell me, is this all like boring, like stuff everyone knows, or is this completely new? Phobo Malone says, so high level, what are the benefits of currying? And is this some functional language specific feature? So currying, I think, languages like JavaScript, you can have a curry function. It's just you have to manually curry a function to do it. If a function takes multiple arguments, you're going to have to manually do that. Whereas in Haskell, it's just automatically done. The reason why it's helpful is, do we have map? Haven't we defined it yet? It looks like it. Okay, so let's think about map. So let's say I have a list. Thank you for the question. That's good. I mean, it would be really easy to just start talking about the language and not talk about why any of this is useful. I don't know if I'm the most qualified to answer that, but I'll do my best. So if I have a list, let's say I want to add 1 to every element in the list. Well, I can create an add 1 function by basically currying. So plus takes 2 arguments. So I look at the plus operator, and I have to wrap it in parentheses because it's an infix operator. It's meant to go in between its arguments. It should take 2 arguments, right? But I can just give it 1 argument. So I can say add 1 equals plus 1. So if I look at add 1 here, add 1 is a function that takes a single argument and returns an argument. So I give it 3, it should return 4. So in this instance, the plus, we curried the plus operator, or was automatically curried for us. So so last time I demonstrated this in JavaScript, and I think I can do it quickly again. It's kind of like saying function add x. This function returns a new function. Bad, I can't write JavaScript apparently. And then that function that we're returning returns x plus y, not yield. Okay. So I can do this where say add 1 equals add applied to 1, and then I have this function and I can apply it to 4 and get 5. So I could, manually write this kind of function, but now if I try to pass 2 arguments to it, what does that actually work? Oh yeah, I think because JavaScript is just going to ignore any superfluous arguments. That's funny. But you see that it ignored this second argument. So so the reason that would be useful is I might have some like higher abstraction, like a function that's more significant, not just adding numbers, but it might take a configuration and take a database or something. And I want to apply that configuration to like multiple databases. So I could pass this function the configuration and then store that as a new function. And then now I just have to pass it a database. Does that make sense? Hopefully that's helpful. Or yeah, I mean the course is gonna demonstrate some of the power of currying. So okay, so we did head or product. We kind of already talked about this, right? So we have a list like 1, 2, nil. We're saying we want to replace the cons operator with this multiply operator, and we want to replace the nil with 1. And then we evaluate this expression, and we get the product of every element in the list. So if I demonstrate, actually I can just do this, right? Product. Why does it not like that? Oh, I'm in JavaScript, that's why. Okay. Yeah. And actually, there's some currying going on here too, right? So product is supposed to take an argument. So it should take some argument like x's or nums, and then we should say nums over here, right? So we say this, well, I have to define nums. Sorry everyone, I'm having trouble typing today. Okay. So that's my list. And if I fold right takes 3 arguments. It takes some function. It takes a starting value, and it takes a list. And so if we go back up to, actually I can just here fold right. It takes a function from A to B to B. It takes a B. It takes a list of A's and then returns a B. So let's break this down. A to B is like multiply. Takes two arguments, an A and a B, and returns a B. It takes some default B value, in this case 1. It takes a list, which is our nums, and it returns a B. So if it's, in the case it's like a nil list, we just return the B that we're given. So we always have some B to return. But there is some currying going on here, right? Because we're saying this value, product given a value, list of integers, should return an integer. But this should evaluate to an integer, and that integer is equal to this integer. That's kind of one way you can conceptualize what we're saying. But just like in algebra, if you had like x plus z equals y plus z, you can just subtract the z from both sides, and you're left with x equals y, right? So we can actually remove nums here from both sides. So before we were saying, I think that's why I have this comment here, this integer is equal to this integer, but since x is the same on both sides, we can just say this function is equal to this function. In this case, fold right applied to 2 arguments is like a curried function. It's still waiting for its last argument, which is some list. So if I say, my func is equal to fold right multiply 1, look at the type of my func. It takes a list B and returns a B, and that should map up exactly with product. It takes a list of integer and returns an integer. I hope that helps. The Pluminator says, I think it maps nicely to the Haskell compiler's model programming, which I believe is based on lambda calculus, where there are only single argument functions. Correct, right. So Yeah, lambda calculus is something that Haskell Curry developed, which I think there's a lot of stuff out there about it on YouTube. So maybe I shouldn't dive into the little I know about it. But it was basically just this minimal way to express logic. So actually, I think it was like Alonzo Church or someone like this in the same academic setting as Haskell Curry that basically showed that lambda calculus was just as powerful as Alan Turing's concept of a Turing machine. So basically, you can compute anything with lambda calculus, which is it's basically all it is functions, variables, and function application, if I remember correctly. It's kind of hard to believe that that's possible, but it is. Actually, I'm kind of tempted to dive in to something I worked on. There's something called the SKI combinators. Maybe I will dive into this because it'll be fun. So a combinator is just like a way to manipulate a function. So maybe I shouldn't dive into this. Yeah. Well, it's going to be a little esoteric, isn't it? Wondering if I should talk about this or not. So maybe I'll try and explain it without going into like really difficult terms. So we can conceptualize 0 as like taking a function and some value, and just applying the function 0 times. It's kind of a weird way to think about numbers, but you could do that. Like let's say if all I care about is the effect, right? So I have this function log, and I want to use this function some number of times. So if I say 0 log and some element, some value 1, 0 is not defined, right? So let me just define this entire file. 0 defined. Okay, good. So if I pass log and 1 to 0, it returns the element, but it hasn't actually logged it. I think I can prove by saying x equals. Yeah, didn't log anything. But if I pass 1, if I pass a function to 1 and a value, and I apply that function once. See, working right? I think maybe it has to be. Oh, right. It's all curried, so I have to do it like so. I have to say that. And the reason it's twice is because it's 1 is what it's evaluates to, and 1 is, so maybe I have to do like x equals. So the network error. Can you guys still hear me? Which was telling me there's network errors. I think we're good. Yeah, so maybe this is too esoteric, but basically what I wanted to demonstrate is you could conceptualize numbers in this way. Yeah, I didn't define 3. So I could add numbers in this way. So I could say plus 1 to some function and some value. And let's see, what should this do? this should log this number 3 times, and actually we'll see it 4 times because 1 will be what it evaluates to. Yeah. And so this literally, there's no numbers defined here. It's just functions, and like 1 is a function that takes a function that takes a value that applies that function to that value. So yeah, anyways, I'll digress from that, I guess. But I just noticed that JavaScript's like arrow function syntax lined up really nicely with this church encoding. So I could like kind of copy and paste these and just translate it into JavaScript. And that's more or less what I did. And literally, that's all lambda calculus is like variables, functions, and function applications. There's not even like numbers. You can just like build your own numbers. So yeah, and then there's something called the like SKI combinators, and this was an even smaller expression of not only is lambda calculus enough to do any computation, just these 3 functions you can calculate anything. And actually I is kind of redundant, right? Because I is just the identity function. It just returns what it was given. K is like the constant function in Haskell, where it takes 2 arguments and returns its first argument. So you can actually construct I out of S and K, which is really bizarre. So like, I think I cheated here a little bit and used this plus function from above. But yeah, if you're interested, you can read about the SKI combinators. And yeah, so I'm gonna digress back to Haskell now, I think. But thanks for indulging me in that. So why did we talk about this? I think we were trying to discuss like why currying would be helpful. Like why would you want to curry things? And it's because it allows you to partially apply things, and then it's like you've defined a new function. You've just given it some starting value to work from, and you can just start composing things together, and you can build arbitrarily complex logic just using higher order functions like that. So maybe that's a little bit of motivation for why something like this. Yeah, I think you'll have to take a little bit on faith and just continue with the course to see that for yourself. Let's keep going though. we'll come back down to the earth now and try to be a little bit more grounded. So fold right. So we implemented this exercise for sum, which is just folding the plus operator over a list with a starting value of 0. We also did length. So length is an interesting case because we don't actually care about the values in the list. We really only care about the structure of the list. So like actually this property test here kind of gives it away. So this expression is kind of saying const1, mapping this const1 function over a list basically would turn the entire list into ones. Would take some list and return a new list of the same length that's just all ones. Let's do that. Have to do this. Yeah. And then so my list was 2 elements long, and this function would return a new list of 2 elements long, but everything is a 1, and then sum those together, and that's the length. So this kind of gives it away, but because we could just like copy this and paste it, but let's use fold right instead. We said we'd start with 0, and then what function are we going to fold over the list? Well, basically we're using const. We're just saying ignore the element of the list, and the second value will be our starting value of 0, and then add 1 to that. So that's kind of like our accumulator. So did I demonstrate down here? I think I did at some point. So I think I'll actually change to const 1. I think that's a little bit cooler looking. Does that work? No, it has to be const. Would it have to be const plus 1? Let's see, let me undo a little bit. This actually would take two arguments, right? And we ignore the first argument, and we add 1 to the second argument, right? Yeah, compose with plus. So we just say maybe I should do my handy like what I always do when I like get a little bit stuck is use this typed hole. So basically this underscore is just saying like tell me what to put here, and saying to do should be an int. So the int should be y plus 1, right? Because we don't care about the element of the list. I think that's right. Okay, that works. But then we can simplify this, right? Because plus 1. So it's kind of the same as saying 1 plus y. And then if I wrap this in parentheses, I can just like, I have this expression again where I'm saying like the function with x and y same as 1 plus y, is that right? And then I can kind of remove this from both sides. I think that's right. But I might need to compose it something. See, is that gonna work? Okay. Yeah, that works. So how can I change this even further to where I just like flip const or something? Yeah, so it's even telling me, H1's telling me use const 1 plus. So great. Okay, cool. And I forgot I also have test here, so I can say length test. No, I have to add it. List test. Test length test. Yeah. So does everyone understand this? So const, let's look at const. I haven't explained that. Const takes an A and a B and returns an A. So it basically just ignores the second argument. You might say, well, why is that useful? Well, it's very useful right here in situations where you don't care about one of the arguments. So what we're saying is const, the first argument to const is this function, 1 plus something. And then the second argument is like the element of the list, which we don't care about. Const ignores it. And then, so this evaluates to just this. It just evaluates to +1. So basically we're just folding +1 over the list. And we're using const to ignore one of the elements. Brave Slime TV, that would work with string length since they are list of chars if you want to do that with non-nums. I guess are we talking about the composing with plus, perhaps? Cool. So let's get into some new exercises. We also did map last time, which is basically cons composed with a given function. So if we look at, so remember our intuition for fold right is constructor replacement. So if we have a list 1, 2, nil, and we want to replace the cons with append or cons after a function. So it's like, it's a little weird, but it's like saying replace this with adding 10 and consing. So it's like add 10 to this and then append it to the next element, which is add 10 to this and append it to the next element. So you basically deconstruct the list into its elements, apply some function to each thing, and then append it all back together. Pretty sweet. Brave Slime TV is the length function. If you want, okay, so length function, if we were working with strings, because there'd be a list of characters. I guess I'm not connecting all the dots there. I think that's okay. We'll be doing stuff with strings later. Okay, finally. Okay, let's do a new function. So I just finally finished kind of going over what we did so far in list. So let's do a filter function. So filter takes a function of some that takes an element of some type A and returns a Boolean, and it takes a list of A's and then returns presumably some smaller list of A's, or the same list if they all match the predicate. So this is like a predicate we're going to check each element of the list with, and if this is true, then we we should add it to this new list. So I'm just going to take the approach from that Brian McKenna YouTube stream and just go with the typed whole approach. So P for predicate here is the first argument, X's is the list, and then I'm going to just throw a to-do in here. And it tells me the to-do should be a list A. And if I scroll up to one of my comments here, that our intuition for dealing with lists is we want an array of the same length, we use map. If we want to go to small array, we use filter, which is what we're defining now, so we can't really use it yet. But if we want to go from an array to some value, which hint might be an array, then we should immediately be thinking of reduce or fold right. So that's kind of the first thing to think of, like when dealing with lists. So I'm just going to throw this here, fold right with holes, starting with underscore, cons and nil, and then x's. But I can go ahead and edit reduce this, and hlint will tell me you can just reduce the x's on each side. So I will go ahead and do that. Okay, reload. Did it too fast for the formatter. Okay, cons. Cons should be a function that takes an A and a list A and returns a list A. And nil should be a list A. Well, if we filter an empty list, we should return an empty list, right? So, sorry, scroll up. So my intuition is, what do we want to replace nil with? Well, we want to replace it with nil. When we were summing, we wanted to replace it with 0 because we want to start with an accumulator of 0. Sorry, sum there. And then product, we want to start with 1 because a number times 1 is itself. I could be wrong. That's my intuition. So then, what do you do with cons? So I'm just going to break it down, go further with the typed whole approach. So it takes an A and a list A. I'm going to call it X and X's for a to-do. Reload. Okay, so my to-do should be a list A. So I need to construct a list A here. I have one. This is going to be my default, nil. And I have this element X, and I have this predicate. So these line up pretty nicely. Predicate is a function that takes an A and returns a bool, and I have an A. It's this X of type A. So maybe what I'll do is I'm going to reformat here a little bit so I can see. I'll just say let y equal be applied to X in to do. So now I can see what y would be. It should be a Boolean, right? So now to do still needs to be a list A, but now I have this y here, which is a Boolean. So we haven't really gone over if expressions yet, but it's just basically like any other language for the most part. So so I've run a predicate on some element X. So I can say if y, yes, spacing, all the spacing is gonna collapse here in a second. We'll simplify it, but for now, it's like if, then, else, I think. See if the auto formatter will help me. Yeah, okay. So if y is true, that means that the element of this list matches the predicate. So then what do we want to do with it? We want to add it to the list, right? So then like X appended to X's, I think. Because this would be, the starting value would be nil. So otherwise, it doesn't, so we just return our starting list, X's. Does that make sense to everyone? That's super complicated and confusing. They're basically saying filter is a function that its first argument is a predicate function. Second argument is a list. We're going to fold over that list, starting with nil, and then we check the last element of the list and feed it into this predicate, which yields some Boolean value. If that Boolean value is true, that means it matched our predicate. We want to keep it in our list. So I'm going to append it to our accumulator list, which starts out as nil. If it doesn't match, then just return our accumulator list. And then, so the next time this runs, it's going to loop through. This will no longer be nil. It'll be well, if one of the elements matches, it'll be this new list. So let's test this. So first, let's demonstrate that we have this helper function even that I believe is defined down here somewhere. It's not an exercise and not something that we defined. Just so we can do filter even over this list. Not in scope. What did I do wrong? Okay, I don't know what I just need to refresh. That works. Let's try odd. Okay, that also works. So I'm just going to clean this up a little bit. We don't really need this temporary variable y. So I'm just going to replace y with px. And I can eat this let expression out of existence. I think I can even like inline this, right? I don't know. Is that really ugly to have? I don't know. Usually I wouldn't be this far zoomed in, so I'll probably just leave it like that. Well, maybe for y'all, I'll put it like this. Yeah, I'm in the South. I say y'all sometimes, can't help it. It's just an effective contraction. Okay, so append to list to a new list. So we're defining our own infix operator here. You can see because the parens wrapped around it. So, which is pretty weird. Like, let's see, let's do something for fun. My new function, which is triple dollar signs, will take some value and it. No, it has to take two values, right? Dumb. We'll cube each argument and add them together. That sounds like a fun function. So now, but because I've wrapped it in parens like this is x, so I can say, oh shoot, now I'm gonna have to do math to make sure it works correctly. Okay, 2 cubed is 8, 3 cubed is 9, so 8 times, wait, stupid, 8 times, oh, they're added together. Oh yeah, 3 cubed is 27, okay. Yeah, so this is a way we can define our own infix operators by wrapping them in parens, and then they go between arguments like this. So that's what we're doing with the plus here. We're going to take two lists and return a list. So x's, y's, and u. I have so like it feels so weird to like not. My instinct is just like, oh, we'll just append y's to x's, but it's like that's what I'm defining. So I guess I have to use. I guess I have to use fold right again. And what am I going to fold over? I'm going to fold over x's, I think. And nil. I'm going to replace nil with y's. Because that'll be like, well, y's will just be my accumulator. Then I'll loop over x's and just like append it each time. I think. So fold right will take an x and a y. Oh, it'll take an x and y is prime, just so I'm not overshadowing. So it's basically going to take this accumulator value, and I just want to append it y's prime. Maybe. Or a test value in here. Aha! Huzzah! Let's see what h-lens tells me. Avoid lambda. Why not just append? Yeah, so that's pretty sweet. So it's like, you can just remove all of this. I have to wait for the formatting. Sometimes this is slow. Okay, still works. Yeah, so that's pretty sweet. It's just y's is our new nil. Then we fold over x's and just append each one. And I think we can like do something fancy here and like flip the arguments. So like we can almost edit reduce. Whoops. Edit reduce this. Like if this x's was here, then we could just remove it from both sides. And I think we can if we flip this like so. Am I crazy? Formatting. MacBook is from 2013. So does this still work? It still works. Okay, so let me explain flip. So flip takes a function which takes an A and a B, returns a C, and then it takes a B and an A and returns a C. So it's like take this function and return this function. That's the way I'm thinking about it. So I'm kind of thinking about it like this. So what would be a good way to demonstrate this? So like if we did 3 minus 1, that's 2. But if we flip minus and give it 3 and 1, it's actually going to do 1 minus 3. So it's just like taking the first argument, putting it in the second position, taking the second position, put it in the first argument. Yeah, that's pretty cool. Okay. So flatten, probably going to be similar. We take a list of list A and we return a list A. We just pattern match here. So we just say like, we're given nil, just return nil. Otherwise, should have like x's, y's. So this first element, so this is a list of lists. So if the list of lists is empty, there's nothing to flatten. Return nil. But if the list of list has elements, this first element is a list, x's. This is a tail. The y's would be a list of lists. So then I think I just I just need to loop over them and append. Maybe we should use can we use fold left here? We've used fold right for everything. Like, I don't know if I've ever used fold left because I always think to use fold right. Fold left. Myself. BAB. So it's gonna be backwards though. That's what I'm concerned about. Fold left. And no. Let me see if I just do. Oh, but it's not. Am I gonna fold over? Maybe I just leave this as list. Then say nil, and then the arguments to this are gonna be B and A. So the accumulator. The first element of the list, which is a list. So maybe I should call this Y's. Then this is going to be an X. Oh, it's actually X's. I think it's going to be backwards because if I append this to ACK, it's going to take the first list, append it to nil, the next one. Yeah, so let's just, yeah, I think this is going to be backwards. I end up always using fold right. Yeah, backwards. Just like appending stuff, it just makes more sense if you're going from the right. I need to change this. We'll go back to calling this X's, and then even though X is a list, X basically later, then just append X. Bam, there we go. And this is basically just append. Cool, so we're just folding over, and then we can even how to reduce this, right? No. Oh, because the pattern matching. But fold right should already take care of nil. Then see. Ah, more matter. I saved too many times for the formatter to keep up. But yeah, that still works. Okay, cool. So it's just folding. That's crazy. I mean, this is one of the reasons I think Haskell is so cool. It's like, it's so expressive. Like, sometimes you're too smart for your own good, and you start thinking about how to implement something, and then you come up with some implementation, works, and then you reduce it, and you keep reducing it down to just this like terse expression. It's great. So we're just folding a list of lists and appending each one. So yeah, I guess if we just go back to our constructor replacement example, it's like if I have 1, 2, nil, and that itself is part of a bigger list for nil, nil. So it's a list of lists here. Then I'm just replacing nil with nil, and I replace this constructor with append. Yeah. So then it becomes yeah. Oh, cool. Like that. Okay, flat map. See, how many more do we have to go here? Deck optional. There's got a few more. I think not reverse is the last one. See how many we can knock out. Okay, flat map. Take a function that takes an A and returns a list B, a list A, and return a list B. Basically, you take a list of A's, break that down into a bunch of elements, just A's, and then turn all of those A's into lists. Then we have a list of lists, and then we need to flatten it. So X is, are you literally just going to flatten? I think we just do this, where we say map F over the list of A's. Then this will be a list of lists, and then we flatten it. So I should do it this way since we haven't talked about $sign yet. Flat map. That compiled, so let's see. Run this test. Also, I forgot to run the test for flatten. Okay, good. Flat map seems to work. Yeah, it makes sense, right? Map, then flat map. But I think we can be even clever about this, and so maybe we'll talk about $sign. So $sign is basically a way to defer evaluation. That's the way I think about it. $sign takes a function a to b, takes an a and returns. So it's just like function application. So it's just saying apply flatten to everything that comes after this $sign. So if we did this, then we basically have to wrap this in parens because we want flatten to operate, like the entire argument is this expression, not just map. So because I guess it's left associative, right associative, I don't know. It might be interpreted like this. So we can add this $sign to say basically, maybe my noob way of thinking was like everything to the right of the $sign. Evaluate this first before then doing flatten, and that should work. Cool. Best flat map. Okay, that still works. But then we see that there's f and x's on both sides of this again. It'll work if I wrap it in friends. Yeah, I think it doesn't. Okay. I was hoping that might be might help explain a little bit better. But basically, we can use a composition instead of this $sign. So we can say compose, flatten, and map together into a single function. So basically, this is now a function that maps something and then flattens it. That should work. No? I guess it really doesn't like these arguments still being here, because I think if I just remove these arguments, it'll work. I think. No. Not work. Maybe because. Oh, oh, I think I understand. So we have to pass this f to map. So I think that's what it is. We can compose this much together. Because I don't need the brackets. Files. Yeah, okay, that passes. So basically, we can't just compose map and flatten. We have to provide map with a function, basically a function to map over things with. So like compose map of f with flatten. So like this takes flatten f is a function that takes a list, maps f over it, and then flattens it. Yeah, okay. Flatten again. Flatten a list of lists to a list again. However, this time use the flat map function that you just wrote. So it's just like when a flat map over x is provided a function, but we don't want to do anything to it. Just use ID. ID is a function that just returns what is given. Going to speed up a little bit here. I'm getting test button. Cool. Yeah, so flatten again is just like We already made a flatten, which is just holding the append over list. But this is just demonstrating that um, we can use this to just define flat map. I guess we could define flat map in terms of fold right, and then we could define flatten in terms of flat map. Kind of interesting. To map this ID function over list, which doesn't do anything, each element, and then flatten it. Peak optional. Convert a list of optional values to an optional list of values. So I accidentally skipped the optional module, and I'm going to go over it next. So I think maybe I won't spend too much time talking about this. So we have a list of optional A's. I'm going to go to optional list of A's. Optional A's. The option. We have to do this first. Optional. Apply optional. Tricky. Any help? List of optional A's. When in doubt, we have a list. Fold over it. Um, let's see. Found hole. Pawns takes an optional A and an optional. Optional. Nil should be optional. So again, I know we haven't talked about this one, but I can construct an optional list of A by just saying empty. So I think that's my my nil case. Empty. And then my cons here should take an optional A and optional A's. Pluminator. Oh, I missed reverse. I wanted to show off my clever implementation using bold right. We actually haven't done reverse yet. Have we? No, we haven't done reverse yet. It's coming up. But if you don't want to stay on until then, I understand. It's getting late. So I mean, if you want to show me your reverse station now, that'd be awesome. Yeah, it's like the sequel optional thing is like, it's kind of odd. Like we're just like chilling here with lists. It's like, oh, we're just gonna hold, and then it's like drops this bomb on us. Probably because I haven't done the optional thing yet. I forget how to do it. So let's look at reverse. So we take x's. We have to reverse the x's. What do we do? What's your clever implementation? Bold right? I guess if we want to reverse a nil list, nil's our default. Oh, you can wear it. You can say Illuminator saying he can stay or she can stay. They can stay. Sorry. And we can come back to it, I guess. Yeah, if you want to talk about it now, we can. Seek optional. So yeah, so it's like flipping this type. So it's like a list of optional, and we're going to go to an optional value of list. The cons. Oh, I need to first. I need to put this back. Find. So it compiles. Sorry. Okay. We have this OA and OAS. We need to construct an optional list out of it. So I guess we just pattern match. Like it's either I'm just going to say let f and just going to create like a helper function for this. So this OA is either from this optional type, it's either full or empty. So if it's empty, then Illuminator says he can use the combinators you already defined in optional. The problem is I skipped this module, and because the README, like it said like start with these. I skipped over this paragraph and I said start with these and then go to these. So maybe what the right thing to do now is just like skip this, seek optional, and come back to it later. But I'm like just so tempted to just like knock it out. I think what we want to do is like if this is optional, it's empty, you just return x's. And if it's full of something, then maybe do we have to unwrap this one too? Like full x's. Then we return like full x appended to x's. Then we say this is like f. Non-exhaustive patterns in f. Yeah, because it would be this is empty. Then we have to return empty, I guess. I guess we could just say this. So I'm actually going to do that. Oh, that works. So if we do seek optional and there's an empty somewhere in the list, we return empty. Doesn't look right. Which always returns empty. Maybe this isn't right. Maybe we need to do all 4 patterns. So if this is full x, we do, yeah, full x into nil. Yeah, okay. So basically, yeah, we'll go back and do the optional module. Sorry, everyone. But basically what's happening here is just like optional, just like list is either nil or some list, optional is like either empty or a full, like basically like a list of one element that way. So this is saying we have a list of optional values. You can almost think of it as like a list of lists. And we need to check, we're going to fold right over them. And then if we run this over an empty list, so it's a list. Basically, if there's any empty element, then we return empty. So it's like we had a list of lists, and any of the lists inside of the outer list was empty. Just want to return an empty list. But if all of them have elements, then flatten it, basically. So that's kind of what this is saying. Is like full 1, full 10. Then this is a list of optional elements, and we want to return an optional list. So yeah, anyways, we'll just move on, and then y'all remember to come back to that once it's optional. Find the first element of the list matching the predicate. E is a predicate. Optional here. Maybe I do want to use bold left here. X is starting value. I'll say is empty because it needs to be an optional. And I'll apply the predicate to X. That's true. Then turn full X. Else. I don't know if I can use full left. In this test, it's going to say, I'm going to check on an infinite list. Yeah, because it's like if X isn't if PX is false, then we want to run find unlike the rest of the list. Would that be a horrible idea? I'm shadowing X. Y is find Y is expected type. Let's state optional A actual type. Yeah, I think this recursive thing. Let's try fold right again. Const optional A. Nader says fold left already recurses, so your cons should probably not recurse. Yeah. Good. Also getting tired now, so Okay, so I have an optional A, an A, E. Say A, and so if it matches, return full. Doesn't match. I have this. I think I have the original list. Then I have this optional A. Gosh, I'm really forgetting. Pluminator's giving me a hint. Your initial version looked fine until you started cursing. Have more than one argument. Okay, so let me go back. The head. I mean, it's pretty similar, right? So fold left. PA. If PA, then so if the first element, except I think in this fold left it would be first. So then if A matches, then we return full. If it doesn't, then we need to search the rest of the list. But I don't know how to do that without like recursing. Fold right is still the correct fold though. Oh, okay. Yeah, as it usually is, yeah. Learning that. Match the types. I just return the empty. Yeah, so I have this OA, so I can make a compile. I don't know why that doesn't feel like it'll work to me. Does that work? Skeptical. Fine, even. An odd, full one. That seems to work. Let's try the infinite one. Hey, it works. Hey, thank you, Pluminator. Appreciate that. So let me try to think through this because fold right. So this empty one, so the first time it loops through. So A would be like the rightmost element. OA would be empty. So we check that element. If it matches, then our new accumulator is full A. Otherwise, just return this empty. Then the next time, this just stays empty every time. So if we don't find anything, we return empty. But the reason it works on an infinite list is why? Maybe that goes back to the last video I was talking about how I was waxing eloquent about how like fold right is constructor replacement. It's not actually folding from the right because it works on infinite lists, and then I tested it on an infinite list and it totally didn't work. So um but maybe this is why this is basically demonstrating that it actually is not having to reach the end of the list in order to recur. It actually is like constructor replace. It's got to be short circuiting somewhere, right? Error says that's because it's fold right. Not sure I follow what you're saying. Full A. So I'm gonna walk through an example to try to convince myself. Find even. Reason it works in infinite lists is what you said essentially. Maybe I explained it and didn't understand what I explained. So I guess what I'm thinking is if it's fold right, like if this was an infinite list, you would just never reach the end in order to start folding. But if it's constructor replacement, then you're replacing this append. Well, we're replacing the nil with empty, and then we replace this with basically some function that takes two arguments. Oops. It checks its first argument against this predicate. If it's true, this would evaluate in full 3. If it's false, it's just empty. So I guess it actually does end up starting from the left, and it's like, if this is true, then it's a full 1, and then just so it just would like return full 1 here. Solve. Yeah, I guess I don't fully understand that. In Vitel lists. Here we go. Why does fold right work for infinite lists? I was under the impression that fold right starts from the end of the list and works backwards. So I imagined what right associative means. So I'm confused that the following works for infinite lists. Hey, it's probably from this course. Yeah, it's exactly the same function. Yeah, and this is the property test. Funny. I did some searching and found this post. Fortunately, the accepted answer is not particularly helpful. Let check xy if x is greater than 10, x else y. Check takes two arguments, but might not use the second argument. Haskell is lazy. This means the second argument may never be evaluated. Aha. There we go. The laziness lets us skip the possibly infinite amount of work. Ah, now it's becoming clear. Now let's step through fold R, check 0. This forces us to evaluate from the top down. See now. Okay, because this is false. Ah, okay, I see. So it's like we might never touch y. If x suits us, then we just return it. If it doesn't, then we return y, which is like recursive. So if the predicate matches the first element, then we return it. Otherwise, we return this thing, which I guess is an infinite list. The reason I was confused is I was just thinking that this was empty. So it's like the first run through saying like constructor replacement. So no, because that's if you were actually starting from the right. Ah, okay. We're not actually starting from the right, which is what the the function name would lead you to believe. So we are starting from the left in its constructor replacement. So if one doesn't suit our needs, now we need to continue to the second, the OA here, basically the second argument to this function, which this, then we need to evaluate it. Okay. Okay, I think I finally understand fold right now. That's helpful. See if I can bang out these last couple ones. Trying to get to reverse, I promise. I mean, denotational, semantically, you are starting from the right. Yeah. Yeah, I see what you're saying. Just like with the append example, like when we use fold left, it was backwards. We had to use fold right because you're appending stuff to the right. Greater than length 4. I think I remember from the first time I did this that there's a cheap answer to this, which is just pattern matching, where we say pattern match on a list with 5 elements. So this would be 1, 2, 3, 4. Fifth element, and then the last would be nil. I think. And if that pattern matches, we return true. Otherwise, any other pattern is going to be less than this because the last element would fail, so that's false. Test greater than 4 test. Okay, yeah, that works. So if I take one of these away, probably should fail. Yeah, failed length of 4. So that's the edge case. These are, so it's greater than 4, so there has to be 5 elements, and then the last one is just for the terminal case, like nil. Let's also test our find test. Yeah. Reverse, here we go. We got fold right, cons, and nil is our empty case. If we reverse an empty list, cons, you gonna tell me your clever solution now, Luminator? Waiting so patiently. Arguments are a, x and x's. Luminator says better get it done with fold left first. Can I not do it with fold right? Is it just much easier? Yeah. You have to go to the end to reverse the list. Yeah, so do we just append? Feels like we would just append to x's x. Because x would be the first element, but we want that to be the end, so we append it to nil. Then x is like the rest of the list. End it, I think. First nil. Verse 1. Huh. No, that doesn't reverse. Fold right version is very interesting challenge. append is a fold. Append is already a fold, so it's in. It's true. Yeah, so fold left. What did I do wrong here? Did I flip the arguments? Rename these. I have a B and an A. Be my starting B. List of A's. The first element of it, like A. I use the polls. Be a list A. I have an A. I have a list A. So is it just like A append to B? See, this feels like it would be the original list to me. That works. Okay. And flip end. Very fitting for reversing. Yeah, I see. Maybe the way to think about it is you're taking the first two values, you're appending them, but you're flipping them. So you flip and append. Then yeah, okay, I see. So it's like if we have 1, 2, 0, it's like taking these two and I'm gonna flip them and append. Make this longer. And then now I'm gonna take these two and I'm gonna flip those and those, which ends up being reappended. Yeah. Go. Cool. Okay, so now let's try to do it with fold right. Fold right. So list A, you could construct a list A, and we have an X, which is an A. X is a list of A. Reverse cons. I'm trying to follow the comments. Reverse cons. 1 cons 2 cons 3 cons nil becomes 3 cons 2 cons 1 cons nil, which is 3 cons composed with 2 cons composed, etc. 1 cons piped cons pipe cons nil, where pipe is flip composed. Interesting. Let me see if I can explain this or write it out. So we're going to say we have a handy function here that's basically just flip dot dot. Just use that. Is that what you're saying? We need cons in there. So if x and x's, then we want to append like x's to x. I guess the what I was thinking is like we have an x and we have x's. X is the first time around, and this is nil, and this like our 3. So we want to just do x append nil, then x is what I was trying to do before. And this is inefficient because end is already a fold. Let's see if this actually works. Okay, so this actually works. And we should be able to, right? Yeah. So you're saying that this is inefficient because this already has a fold in it. I'm not sure I understand the example you typed out later. So verse cons. Are you saying to like recursively put reverse cons in here? That's like still a double recurse though. The last line is a series of functions applied to nil. I'm just going to copy what I typed out here. Don't mind. I just tried to copy it from different. I'll just type it out. Um, 3 cons posed with. So type to on 3. No. Oh, the right prints, not after no. So so what is the implementation then of this function, the cons function? Do we use the pipe operator? About folding an input list to generate this chain. When I replace this cons, I'll flip compose type. That's what find it. That work? Wow. Yeah. I don't think I understand that. That's pretty cool though. So then basically it's saying this becomes X cons pipe X's maybe. The fold left version is way simpler. But no, this is really cool. I'm trying to understand. So if we define this pipe as flip compose, the input list arg on the left and make it point for each. Oh, like we need X prime here. Or are you saying, sorry. Yep. After reverse. Oh, I see. Yeah, okay, so I have exit. Got this. So fold right, so we get I throw a to do back in here. X's. Okay, so we need to return a list of A's. Y's is like our accumulator. Y is like the last element because we're folding right. Generating a chain of functions. That's the nil function. One cons, pipe two cons, pipe three. Chain of a function applied to nil. Oh, okay. So this composes one cons. Oh, I think I might trying to see. So it's like saying append the first element. This is a function that appends the first element and then compose that with the function that appends the second element to something. But this will happen after this. And then eventually, so we were like basically composing a giant function that just like appends them in reverse order. Okay. I think I understand this conceptually. I'm just having trouble putting that in here. So, because I actually have the last value. Y is the last value in the list. Y's is like the our default like nil. Chain of functions applied to nil. You want to fold over the input list to generate the chain of functions, then apply the chain on nil. Fold over the input list to generate the chain of functions. So okay. So X is F nil there. I mean the nil of functions would be like ID. So ID is correct. So then Okay, so you said start with F nil. F is the I don't know if I understand that. I have the first value. And I just want to construct a chain of function. So then so do I need some, are you saying I need some like thing like this where I have a fold F? But if I have X's, oh no, am I on the on the right track? Where F is a chain of functions you build by folding over X's. Tricky. I have to come back to this at a future date. Yeah, I think that's really cool. Like I think I understand it conceptually is where it's like we're making a function that appends the first element to something. And then we compose that function with so we build a chain of functions by looping over the list. That's where I'm getting lost. It's like how to build that chain. I guess like this thing ID is nil. And if I just replace I can just replace nil with ID. This like create a list of functions though. Cons is suppose our pipe function. I feel like I'm so close to something like this. I don't want to go so way. Okay, for that. First, X is F, where F do I have X's scope here? Stay F. Now I need to fold right. F is a fold right. Now I do fold right. Cons ID X's. Type inferences like bad. Maybe it's better if I do let this in F nil. Not. Oh, I see. So then cons. Huh. Yeah, because the second argument to cons is the ID function. Or the Y is so Y is like the first element of X's. And then I want to create like a chain of functions. Then Y, I'm gonna do this thing. Ended with okay, composed with Z. So then that's where the nil comes in. I think. Holy crap. No. So close. What's not working now? Oh wait, this is the wrong one. Oh shoot. Did it. Dang. Yeah, that's too galaxy brain for me, man. I'm just a Haskell noob. Jeez. That's insane though. Okay, so pipe, this is basically like the elixir pipe, because composition in Haskell is like right to left. So this makes it left to right. So then we're defining a new function f, which is a fold right, but it folds over functions. That's what I got lost on. So no, it folds over integers. But the result of this fold is a function. That's what's so weird. Basically, you're building up closures of like every element of the list of x's. So it's like y is the first element of x's, and z is this function id, and then you're building a function out of y. Jeez. Okay, so then we have this function that appends y to something. We compose that with which, yeah, which would be like id very end, but then it's going to recurse. Wow. Okay. Yeah. So then let's look at it this way. So let's look at it this way. So if we replace null, but do we replace null with id? This here. Yeah, so the result of fold right, so f is like a giant function that appends every element of first order to some value. So I go back to the original reverse a is equals fold right, flip, opposed bonds. Okay. So oh wait, do I just why isn't that a bit of reduction? I don't think it goes there because we're building up this function. ID. Oh, A's. Wow. That is crazy. But then why wouldn't you just like flip this whole thing? Flip that. Now it takes nil first. And then that work? Gotta get the edit reduction in there. No, that's pretty wild. I'm definitely leaving that in here. I feel like yeah, it is. It is way less readable. Yeah. That's really cool though. Thanks for walking me through that. I really appreciate that. I'm sure that was a struggle pair programming through Twitch chat. Maybe not the ideal scenario. But I really appreciate that. I think I learned a lot from that. Oh man, so tired. See, got two more. Yeah, I think I'm I think I might have to call it a night. Oh wait, produce is already implemented. Like some helper function. We're so close to the end. I'm just gonna like go through this. Twitch head voice. Yeah, I agree. Like some combination of Clubhouse and Twitch. Yeah, we could start a Discord. Yeah, we could. If wife is yelling at me. Yeah, yeah. Take off, man. But if you want to join Discord, I'm on the functional programming Discord. Maybe find me there. There's a Haskell beginners channel. Yeah, thanks for hanging out, Pluminator. I'll see you later. I am just going to go over this last exercise. So this function is called not reverse, and function is called not reverse, and it's asking us do anything other than reverse a list possible. So I think the point of this exercise is trying to teach you the power of type signatures. So is it possible to do anything other than reversing here? Well, so the first test says not reverse of nil is empty list. I mean, I don't know what else I can do. Fold right. Start with that. Ones. Throw the nil in there because it says not reverse of nil is nil. That. Cons should be A in a list phase. Maybe we also need to look at these prop tests. Test not reverse X Y. Yeah. Okay. So types. This prop test is saying let types equal X. where X is type of types is X. Not reverse X. Let's not reverse Y. Not reverse Y appended to X. So if I just make this compile by putting what happens is the prop tests fail. Test. Test. Not seeing. Okay. Yeah, lost. Optional. Uh-oh. Can't get oh. Okay. Try not reverse. No. Yeah, so it's always just so append A to A's. That work. But then can't get the test to work though. So how am I I did it? Oh, it's just called reverse test. That's for the regular reverse. So what if we just put reverse? Yeah. So I think what basically what this is trying to say is that this is so weird that it's like I keep losing target set or whatever. But I think what this is trying to say is like we have this type, takes a list, returns a list, and then that type signature combined with the property tests saying not reversing an empty list returns an empty list, and then not reverse x plus not reverse y or append should equal not reversing y appended to x. So then if we look at this, like if x is equal to 1, 2, and y is equal to 4, this property test is saying calling this function on x and then not reversing x plus not reversing y is not reversing both of these together. So basically f of x appended to f of y equal to f y x, and the only thing that like pass is verse. So I think it's just trying to demonstrate the power of the combination of a function signature and like property tests. Like you can basically um, dictate what the implementation of the. And I think this concept is called parametricity or parametricity. Abstract property. By being a low. Parametricity. So I guess maybe we're told like we're giving a list of any types, a list of element of any types, and we have to return a list of that same elements of that same type. And then we're told that applying this function some list x, appending that to some list y should be. It's like we're not told, we still don't know what any of these elements are. So it's not like like if we knew they were numbers, then we consider like doing some kind of mathematical operation. Or if we knew it was a list of lists, we like, but we literally don't. This list could be anything. So the only thing we have to go off of is their structure and like the properties of tests. And I think that's what parametricity is. Like type information, that kind of information. All right, that was the list module. Thanks to everyone who watched, and thanks to Peter for walking me through this really galaxy brain version of verse. That was, I'll have to think about that one a little bit more. I hope that wasn't boring for people to watch me sit there and struggle with. Um, yeah, I think next time um, I'll go back and do optional, and what I'll do, I think, I don't think the test actually pass on this. Test is optional. Option. And I think, in fact, it's getting stuck in like here. Get out of it. Yeah, so I'll come back to this. Maybe what I'll do is find here everything. So, and so to test the entire module, they of like, so everything pass, optional, fails, expected. Everything else pass. There we go. I'll come back to this after we talk about the optional. Thanks everyone for watching. Really appreciate it.